Bottom line is engineering is all about product development for practical applications. So if you're a good engineer, you should be able to develop products, not just writing papers and attending conferences, but you should be able to develop some products which are useful to community as well as your company. So these are some of the examples. I think satellites you see on the left side, on the right side you see the missile. I think antennas are important for all applications. Then you have a UAV, unmanned aircraft vehicle. So there are antennas there also. And then there is ground station, large antennas like 34-meter reflectors. So all are different types of antennas for different applications. So any communication system, I think antenna is a key component of any communication systems. And on IEEE APS, I think I just want to share this because total about 9,400 members are there. These are paid members. So if you look into the regions, I think 1 to 6 has the highest 3,400 members. And then next comes region 10, which is 3,031, which is almost close, within 10%. So I think region 10 is very important where you are, most of you. And then the Europe is the next one, which has about region 8. So that has about 2,200 members, and region 9 has a small number, 204 members, that is South America's. So region 7 is Canada, so that has about 300 members. So region 10 is very important because that's a fast growing. Probably by next year, I think it will take over region 1 and 6. So there are a lot of focus on region 10 now. I think both India, China, Australia, especially student members are growing at a fast rate. I think India has the largest student branch chapters, just like what you have in Allahabad, I mean NIT. So I think they're very important student branches because IEEE sort of wants the student members, and then a large number of students participate in IEEE activities and organize webinars, conferences like this. So I think that's very important. So total IEEE has about 500,000 members. It's the largest professional body in any field. So it has 210 chapters, 1,400 student members, and 500 IEEE fellows. And it has 4 leading journals, IEEE Transactions, Antennas and Propagation Magazine, and AWPL, Antenna Wireless Letters. And then it has 1 flagship conference, which is IEEE APS-RC conference held every year in the month of July. So there are 40 conferences IEEE supports and workshops worldwide. So if you're organizing any conference in India, I think it supports 2 major conferences, which is MapCon and VAMS. So you can attend those conferences and present papers as well. So if you're not a member, I think you should become a IEEE student member, or if you're faculty or professional engineer, I think if you're not a member, I think it's time to become the member because it pays a lot on the long run. What we get from IEEE is much more what we pay through yearly registration fee. So because you can network with others, you can communicate with professors not within your university, but also worldwide. I think most of the senior people will help you. If you have a question and stuck, I think you can ask them. So I think if you're not a member, I think please consider becoming a member, IEEE member, either AP Society or MTT, Microwave Theory and Techniques, or ComSoc, which is Communication Society. I think there is almost about 38 societies in IEEE, so you can become a member in any one of them, and most of them are multiple members of, like whoever becomes APS, they also want MTT member as well. So. This is the VAMS conference. I just want to show that it is organized during February, March 2024 in Raghu Institute of Technology of Visakhapatnam. So I think all of you, I think it's open for paper submissions. So visit the website. I think its website is given vams2024.com. And then I think consider attending the conference because there are a lot of student travel awards. I think travel is free, accommodation is free in the hostels or dormitories, and food is free. So I think none of the conferences will give you this sort of thing because the focus of VAMS is to encourage students. So I think we have a lot of awards as well. I think out of 25 awards, I think about 15 are given to students. So I think the students are given top priority. So if you're in the final year or third year or second year, I think consider submitting a paper and attending the conference as well. So like I said, antennas plays a key role in day-to-day communication. I think you might have seen antennas on they're needed for radios, cell phones, TVs, TV dishes. You might have seen cars. Nowadays, I think a lot of antennas put on the cars. I think mainly to collision avoidance purposes, etc., and also giving directions while you park the car. So, and also satellites, deep space communications, the probes, aircrafts, missiles, large ground antennas, etc. So a good antenna engineer should be able to develop antennas for any of the applications. I know there's different applications, different requirements, but if you're a good engineer, having some experience in the industry, you should be able to design antennas for any application. You cannot say I can design only patch antennas or monopoles or dipoles. You should be able to design the reflectors, phase arrays, or other antennas, what is needed. What you see here is, we'll talk about more, but on the bottom right, it's a B2 bomber. So you can see there's no antennas you can see because it's all stealthy. So it's all, you cannot identify this aircraft by any radar means because the radar cross section is very, very low. That's how it's made, all this material. So, but there are a lot of almost about 40 antennas, I think, embedded in this structure. So this is a different sort of beast. And then you see the largest ground antenna, that's about 1,000 foot diameter. So there the complexity is a bit different, how you sort of mechanical complexity is much more. And of course, the antenna complexity comes because it's very wideband, ultra wideband antenna system, starting from VHF to almost UHF and up to L band and S band as well. On the middle top, in the middle of top, you see the E3 airborne warning and control system, AVAX, which is antenna is a phased array. It works at 10 gigahertz. It's a slotted array. So you can see it's mounted on a modified Boeing aircraft 707. So this is to give the early warning to ground and ground stations in case of any attack or any other penetrating into the US or any other US controlled areas. On the bottom, I think you can see the 64 meters deep space network antenna. That's very large antenna to communicate with deep space. So typically it's done at S band and the Ka band both, dual band. So there's a tracking system to track objects very closely. And on the top, you see the missile, advanced missile, which I think we are working on now for US military. So you have antennas in all these systems, and you can see how different types of antennas are being used for different applications. So what is engineering? So engineering, I think we all want to join engineering because it's an exciting field and there is a lot of scope for innovation. So like I said, no other antenna is identical. So every requirement is different. So you have to design different antennas. It's not like amplifiers where or LNAs where if you have given a band, I think you have a standard product. So in antennas, there is no standard product. So everything is different. So I need to understand the basics first. And if you understand the basics, I think that's it takes you a long way, and then you can apply your knowledge to design complex systems. So concepts are very important because, like I said, each antenna is different for different applications. So sometimes you need to think outside the box to come up with antenna design that meets the requirements. So always you design given the requirements. So sometimes you fail, but if you don't fail too often, then I think you don't have a job. So failing is not bad, but I think through failures you learn a lot, but at least don't try to do the same mistake again. So that's why in space, actually, we have a lot of checks and balances. So before we launch any satellite, we have to test it like almost like depending on the complexity of the satellites, 9 to 18 months, I think, will be in the test phase. So sometimes we test repeatedly how the performance of the antenna, like BISWAR, isolation, axle ratio, patterns, many times. I'll go through that later. So you need to acquire critical skills. So what are the critical skills? It's not just running some software and designing patch antennas or slot antennas. That's not. I think you should sort of get away from that. I think that skill is important, but that's not the only skill. I think you need to understand the systems. You need to understand the hardware. Hardware is more important than software because that's what you use. The end product is the hardware, right? So, I mean, software is just a means to develop the hardware. So RF, I think you need to have knowledge of amplifiers, microwaves, down converters, up converters, filters, diplexers, etc. That's very important because most of the systems you need to integrate them as part of the antenna hardware, like filters, diplexers, OMTs, polarizers. A lot of hardware you need to design as part of the antenna. So mechanical is also important because whatever you design, when you launch the satellite, it has to withstand a lot of loads because the loads are pretty heavy. Whole vehicle actually shakes quite a bit. I think you have to design for many, mechanically you have to design such that it doesn't fail, vibrations, etc. And a lot of tests I think you need to do before you qualify the hardware. And you need to understand the customer, what customer wants. Sometimes customer wants certain requirements more than other requirements. So you have to adapt your design accordingly. And then what important is work with passion. So it's not like I work like 12 hours or 13 hours, or that's not important. Whatever time you work on your daytime, either 6 hours or 8 hours, doesn't matter, but work with passion. Don't waste your time. And this is very important because most of you are in the learning phase. So it's important to understand the basics and then don't work too hard, but work work smartly. So understand the basics. Whenever you work, I think work with focus on what you're doing. So it makes a big difference. So innovation should be daily routine of engineers. Every day you have to think outside the box and see whether sometimes I think I'll talk about innovation a bit more because that's one of the topics. So this is a quote from late Steve Jobs, who is the CEO of Apple. So innovation distinguishes leaders from followers. So I think you follow your advisor for a while, but then don't follow continuously, then you cannot grow. So then detach from him after a while, I think after you learn, and then you slowly develop your skills and you become a leader at the end. So that's how you should do. So engineer should learn, then apply what he learns or she learns, and then develop systems, antenna systems, then innovate, and then lead. So these are the top qualities of good engineer. And I think a lot of engineers are there, but I think most of, I would say that in industry, even here,
Sir, I think you are muted. Sir, please unmute yourself. You are muted.
Hello. Yes, please unmute yourself.
so can you hear me now?
Yes, sir. Yes.
Yes.
Okay, sorry, I think it by accident. Okay, I think we are on this chart. So I think we have done this. So what is antenna engineering? I think, like I said, you need to have knowledge in several areas. Systems, I think you need to understand, because you design your antenna systems based on requirements coming from systems engineering. Then you need to know RF, which goes on the back end, because you need to interface with amplifiers or LNAs or oscillators or up converters, down converters. So you need to do that. Manufacturing is important because there's a lot of ways you can manufacture a given hardware. So you need to understand the tolerances, whether you want to do 3D printing, or you want electroforming, or you want to machine on the lathe, or there are other methods as well. So mechanical engineering is also, because you need to interface with mechanical engineers. Testing, I think you need to go to ranges, whatever hardware you develop, you take it and you need to test it for RF performance, either through network analyzer, measuring the VSWR, axle ratio, or go to the range and testing the patterns. So those are very important, because if you don't know how the testing is done, it's very hard for you to qualify the product. So at the end, you have to qualify the product. So temperatures you have to qualify, for example, if it is space, mechanically you have to qualify for vibration, etc. So understanding hardware is very important. So at least antennas, there are hundreds of different types of antennas. You need to know most of them, because then only you can see which hardware you want to use for given requirements. So always I say, keep the design simple. People have a tendency to complicate the design. The more complicated it is, the more problems you'll have. So always keep the design simple and make sure that it meets your requirements. So that means in terms of hardware, you have to make sure that what you have is the simple hardware, which is easy to build, which works, and which is lightweight and compact as well, because all these things are important. So antenna subsystem is not just the radiating part. So you have horns, reflectors, etc., phase arrays for radiation purposes. But then you have components like polarizers. It decides what polarization it has. Is it horizontally polarized, vertically polarized, circularly polarized, right-hand circularly polarized, left-hand circularly polarized, or dual polarized. Sometimes you need the dual polarization to increase the capacity. OMT are the more transducers. When you want to both polarizations, you need to use them. Separate the signal into two polarizations, orthogonal, with high isolation. Filters are needed because you need to define the bandwidth and you need to reject the signals coming outside the frequency band. So sometimes you have band pass filters, band stop filters, cavity type filters for high Q. Then you have diplexers where you separate, for example, you want to both the transmit receive from the same antenna. You have to separate the two frequencies, which are separated by 30 to 40%. So you need to develop the hardware, which is very wideband, and also give the isolation. Typically 80 dB isolation is we design for satellites between transmit receive bands. So you need to provide the filtering through diplexers. Sometimes frequency selective surfaces, I think, are used to separate the frequencies, but that's old technology, I would say. Currently, I think we don't need FSS. I think most, some cases you might need, but most cases try to avoid that because it's lossy, and also you can actually do without FSS. I'll show you some hardware because you can, two frequencies you can combine through single feed without FSS. Radomes are important because sometimes you have to protect them thermally. When it goes to very high temperatures or low temperatures, you need to have radomes. BFNs, beamforming networks, when you combine the signals from different feeds into one port, so you need to have the beamforming networks. Waveguides, that's waveguide part interfaces with repeater payload. So sometimes you have rigid waveguide and some flex you need to take away the for mechanical flexibility, you need the flex waveguides as well. So all these things are important components of antenna system. And when you have so many components, I think you don't, you design individually, but then you have to integrate them into single hardware piece. So with minimum flanges, because flanges are lossy as well. So you want to minimize, and they're sometimes heavy as well, mass-wise. So you want to integrate as many components as possible into a single hardware. So design, fab, test, qualify, and deliver. So that is boom to tomb. So if you're an engineer, I think at least a couple of programs you have to go through, where you start the design, you go through fabrication, you go through testing, you qualify the hardware before you fly, and then you deliver to the systems. And then the pleasure you get when your hardware goes into launch and in orbit and working great, I think that gives the greatest satisfaction for any engineer. So we can design all complex systems, but if there's no applications, then there's no point in. You can write papers on that, but that's okay. That's limited. And then the key part is deliver the hardware with complying to all the requirements and within cost and schedule, because launch cannot wait for you. So if it is something you have to deliver in 12 months, you have to probably deliver in 11 months, because then it has to be integrated with other components and delivered to the launch pad. Like I said, experienced engineers should complete 70% of the design within few days. It's not like if you start doing HFSS simulations, different antenna types, see which one matters, it will take like 3 to 4 months, and you cannot wait, that sort of thing. If you're in industry, I think you should be able to complete the design and tell. Sometimes you have to tell within the same day, because system guys, we won't get too much of time to propose. The proposal time is typically 1 month. That means systems have to work, antenna has to work, there are other subsystems, spacecrafts. So all these things have to be designed quickly. So sometimes you should be able to give the performance of the antenna in the meeting itself. So engineering is different. If you're in the academy, I think your main focus is publications. If you're in industry, the main focus is in hardware and patents, product development. And both cases, I think you need to grow professionally. So you need, you become a mentee first. I think you need a mentor. And then you do self-growth, you learn yourself, either reading papers or reading patents or reading some books. And then once I think you attain certain stage, I think you need to start mentoring. So you enter some interns or young engineers, and then you become a leader. So outstanding engineers, I think they can become the leaders, and becoming a leader in industry is very difficult. So you need a lot of dedication, hard work. So those are the qualities of outstanding engineer or the leader. So how to become a leader? like I said, becoming a leader in industry is more difficult. Need to have several skills. So you need to look through research, what people have done. You need to look into what other companies have developed. You need to go through systems, qualification, test, all these. Also, sometimes you need to work with vendors, suppliers. And most of the contracts are given to different suppliers, component-wise, or even the antenna sometimes, if you don't have enough engineering workforce. So you subcontract to some vendors. And mentoring and compassion and hard work and perseverance are needed in the industry. So your work will be recognized by your peers in the industry. So that's basically, I think, if you work a long time in industry and if you do good work, I think you get recognized through industry worldwide. So then you have to, if you're in industry or even academic institute, you need to do innovate. And nowadays, I think India is giving importance to innovations and patents. So I see a lot of Indian universities, I think, working that way, and products as well. And you get national and international recognition. So this is the quote I like from Mokshagunam Visvesvaraya, I think the most recognized engineer in India. So science is about knowing and engineering about doing. So he's a guy responsible by building dams throughout India and storing waters and using it for farming and other purposes. So he's one of the greatest engineers. So how to design antennas? I think this is the first part. I think, like I said, understand the system and system requirements. Communication system you need to understand. So what are the frequency bands and how the system works. So then you derive the antenna requirements. So what are antenna requirements? Typically for the satellite, it's a coverage. What area, what coverage you're covering through your antenna? Is it a map of India or coverage of corners, continental US, or it is a different country, or it's a region, small region, or a spot beam, especially for military purposes. And you need to know the frequency bands, what the frequency bands you're designing. So sometimes even the frequency bands, for example, C-band you design from 3.7 to 4.2 downlink. So you have to design slightly larger band than what you need. The gain, I think what the antenna provides a gain, not at single point, but over the coverage, what is the minimum coverage area gain, and how to maximize the minimum coverage area gain. So that's polarization is important, what polarizations you are providing. Especially if it is CP, then you need a polarizer, so you need to design the polarizers to give a very low cross-pole. Cross-pole discrimination, this is the ratio of the copole signal to cross-pole signal at any point within the coverage. So typically for most of the satellites, that value has to be 33 dB more than. So that means your cross-pole level should be 33 dB below the copole. So that is the requirement you need to meet. If you don't meet that requirement, I think customer won't accept it. So that means you have to design it for almost 40 dB cross-pole levels. So that is very difficult, and you have to design over the bandwidth, whatever, 500 megahertz or 1 gigahertz band. And environmental, so most of the satellites operate very large thermal range. So when the sun shines on the satellite, it gets very hot, up to 180, 190 degrees C. And when the sun is on the back of the satellite, it's cold, it's night for the satellite. So it goes up to minus 160 degrees C. So there's a total variation of almost about 350 degrees C or so. So some of the components are very sensitive to temperature, as we all know, especially the filters. So you have to design them to sustain, to meet the performance over the thermal range, both ambient, hot, cold, and several cycles in between. Power handling, most of the satellites, they have high power, up to 2 kilowatts or sometimes even more. So that means all these components when you design, they should not have small gaps, or they should be should handle the average power as well as the peak power. So RF interface is important because you have to design it as a low loss interface. PIM, passive intermodulation, so that's, I won't talk too much about it, but you can read in my book. So that's also important because you don't want any intermods, because all these satellites have multiple channels. So when these different channels beat against each other, they produce intermods, and you don't want these intermodulated signals falling into the receive bands, because the receive is very sensitive. So you don't want to blow up the LNA. So you have to make sure that you provide enough PIM protection for your hardware. ESD, electrostatic discharge. So when you're in space, it has no atmosphere, so it's all vacuum. So any charge is developed, it gets accumulated over time. So, and then when it reaches a certain stage, everything breaks. It loses the material properties, and then it stops functioning properly. So that's very important. So one of the main reasons we don't use dielectrics in space is because of ESD. So my designs, I don't advise anybody to use dielectrics. So that's why you don't see most of the printed antennas or patches in high gain antennas. Some cases you will see them, but probably the requirements are not that stringent. Mass is very important because every kilograms to launch, it costs about 50,000 US dollars. So mass is very important. So you need to minimize the mass. Size also, because you pack all these satellite payloads into a small volume before you launch. So you need to maintain compact size. Cost is also important, because sometimes you win the proposal based on the cost and performance. And schedule, if you say that, okay, I'll provide my satellite, everything ready for a 24-month schedule, you should sort of meet that schedule. So sometimes you have to work very long hours, sometimes maybe 24 hours in night shifts as well, when the testing comes and when you're lagging behind, because the deadline for the launch won't move. So you have to meet the schedule. So initially you perform once the requirements are given by the systems, and then you derive the antenna requirements, and then you perform trades to see a few antenna configurations which have potential to meet, but don't start with a big list. I think probably my suggestion is start with maybe 3 or 4 antenna configurations, do quick trades, and then select a configuration. So to do that, I think you need knowledge of fundamentals and knowledge of hardware components, what works for what applications, whether it can provide the wide bandwidth, the low crosspole, a lot of antenna configurations. So you need the knowledge of that. So then select the antenna configurations based on the traits, and then you start using the software, either HFSS, to verify your design. Most of the design, I would say, you can do with basic principles. I think I'll show you some of them, how to quickly design antennas, either reflectors or phased arrays or horns. If you start doing only HFSS design, it gets like sometimes actually some cases people 6 months passed and they don't have a design. So that's not encouraged in any industry. So once you select the antenna architecture, then you perform HFSS or CSD missions, POC3D, which is for multipaction high power handling software developed by Spanish scientists. FICO, TICRA is a reflector software. I think probably most of the people I sort of talked in India, they never heard of TICRA, because that's a very widely used software in industry, because most of the antennas are reflector based because of the cost. So then I think you discuss your design with your mechanical engineers, and they also have some input. So you need to make sure that your RF design is manufacturable and mechanically it works. So, and then compare performance with requirements. So whether you comply with all the requirements. So if you don't meet the requirements, then you have to go back and change the design of maybe one particular component or maybe a few components. So we all know how antenna radiates because it basically has a source, a transmission line, and a tapered section, which we call it antenna, because the tapered transition is basically the antenna which interfaces the transmission line and then how it radiates to free space and matches to free space. So it's basically it radiates due to time varying currents, and your time varying currents are produced by charges. And they cause, once you have time varying currents, then you will have electric and magnetic fields. So you can see on the right side how the dipole radiates. So you have positive charges, negative charges on the right side. And then your currents, you see the flow of the currents in the red lines, and then how the E field radiates. So on both sides, because there's no ground plane in this case, it's an ideal dipole. So it radiates both equally on the forward side and backward side. So once you have the dipole, everything radiates in the forward hemisphere with less radiation in the back lobes. So basically you need all these. So antenna is nothing but transmission line plus a taper transition to radiate into. So all these designs we do, maybe hundreds of designs, they're all about taper transition of the antenna, because it has different requirements, how it radiates, what is the gain you need, what is the coverage you need to sort of meet, etc. And some definitions here, isotropic radiator. Basically, it's a point source that radiates equally in all directions. So this is only hypothetical. There's no isotropic radiator that exists, and that's probably most difficult to make because nothing radiates equally without any cross pole. So it has to radiate equally in 4 pi steradians. So that's why it's a dB. It's a relative measure of defining the antenna gain or directivity. So on the bottom, you see directive antenna. So that means all the energy is focused in a small region. The narrower the region becomes, the high, the directivity becomes high. So, or the gain. So gain is nothing but directivity minus antenna losses. So in industry, we don't care about directivity because directivity is how it radiates from the aperture, how efficiently it radiates. But you need to quantify the antenna losses. There are several antenna losses. If you have a reflector, you have RMS. Then you have conductive losses. There are other types of losses, mismatch losses, etc. All these losses you have to quantify. There's also loss due to temperature, so you have to qualify that. The filter losses, etc. All these things you need to quantify, and then you subtract those losses from the directivity. That's antenna gain. So typically most of the specs are related to antenna gain. Then there's a polarization. Typically you need both vertical and horizontal polarization. So for a satellite, you can see on the right hand side the typical coverage of CONUS. So you have a coverage in east, west, and north-south directions, and so all the coverage, the blue curve is basically CONUS coverage, and the red curve is coverage including pointing error, because satellite has certain pointing error. So you need to include that when you design these antennas such that you meet minimum gain requirements, including the pointing error. And if your electric vector is parallel to north-south, then it is a vertical polarization. And when it's parallel to east-west, then that's horizontal polarization. So the definition of polarization is a bit different for satellite applications. So we all know that circular polarization requires both vertical and horizontal polarizations, and then equally, and then both have to be in phase quadrature, so that your electric field vector, as you see through in the direction of propagation, it rotates clockwise, then it's a right-hand circular polarization. If it rotates anti-clockwise, then it's a left-hand circular polarization. So the sense of polarization is very important, because sometimes at least 3 cases where polarization, it's supposed to be a left-hand polarization, but it's designed for right-hand polarization, and people cannot use it because the ground are designed to capture the left-hand polarization. So they have to make some changes to the ground station, and it's sort of, so this sense of polarization you need to measure many times during the test phase of the satellite. So beam types, I think point coverage, because that's basically point A to point B. So point A is on the ground and point B is on the satellite. So basically you communicate between them. Sometimes it's not point to point. It's each beam has certain, it's a pencil beam or spot beam, we call it. So it has certain beam width. So maybe 3 dB beam width or 2 dB beam width to cover a small area, maybe 1 degree or half a degree. So then I think it covers the region on the ground. Then you have area coverage. So most cases, I think you need, like I said, conus coverage, what you see on the bottom. So that's basically the coverage on the ground, what you see, shaped beam coverage. So that's all achieved through shaping of the reflector surface with a single feed. And then it covers not only conus, but also Hawaii and Alaska, which are part of the US regions. So single feed with the shaped reflector can do all these wonders. And you don't need to run any software to analyze the performance. So we have actually Gaussian beam analysis, which was published in 1990, late 1990s. So in IEEE AP magazine. So a lot of people use that to now estimate the minimum directivity or gain for either pencil beam or area coverage beam. So what is a satellite? How it communicates? So you need, you have different types of satellites. On the top left, I think you see the, for mobile satellite communication, large mesh reflectors. And the bottom you see DirecTV type, where you receive the signals on the rooftop dish, and then you get high definition and other lot of TV channels to home. So it's a direct to home broadcast. Satellite is nothing but a relay in space. So its main purpose is to connect people on the ground, either ground to ground or ground to user, or user to user, or user to ground. So sometimes aircrafts it connects. So it's mainly purpose is to connect the people on the ground. And there are different altitude. Most of them are geostationary altitude, the satellite, so that it remains stationary and covers all the time particular region on the ground. So you can see typical geostationary orbit is about 36,000 kilometers above the Earth, and the Earth radius is 6,800 kilometers around. So you can see the angle you get is very small, plus minus 8.7 degrees. You can cover the complete globe, maybe part of the globe, because to cover the whole globe you need 3 satellites. Because if you're in the Pacific region, you cannot cover the Atlantic region. So you have to have 3 satellites as a minimum to provide the global coverage. So when you do that, then the satellites need to talk among themselves. So that's called inter-satellite link. That is typically done at 60 gigahertz. Then the reason also satellite communication is popular, because 1 degree corresponds about 640 kilometers on the ground. So that means it covers a lot of area with a very small angle. So when the angle is small, of course, the gain is going to be high. So that's to compensate for the 4 pi r over lambda free space propagation losses. You need to have a lot of gain on the antenna, on the satellite, as well as on the ground. So typically you see on the bottom, the ground station actually communicates. If it is C-band, typically uplink is for the satellite 6 gigahertz, downlink is 4 gigahertz. So uplink is basically ground station transmits high power signals at 6 gigahertz. So satellite receives, then down converts into lower frequency band, which is called downlink 4 gigahertz, and then transmits a high gain beam on the ground, either to the large reflectors or small users with small dishes. It communicates. So what are the key considerations? I think thermal, I said, has to cover very large temperature ranges. So minus 170 to plus 190 or so. So both hot and cold side. So high power, so it should be able to handle high power. Low PIM, typically minus 135 dBm is the PIM spec typically, but it depends on the frequency band and etc. ESD, electrostatic discharge, that's very important. You need to keep it low or actually nothing. And then it has to meet very stringent cross-pole discrimination requirements of 33 dB. So quality of any communication we know is the signal to noise ratio. So that can be the equation, small equation you have is ERP, effective isotropic radiated power, and then G over T, which is the quality of the receive antenna, gain to noise temperature. Then you have Boltzmann constant, which relates noise to or signal to any temperature. SL is a large number, negative number. So it's a free space attenuation, which is over 36,000 kilometers. For example, if you're operating at 30 gigahertz, then you have almost 220 dB loss. That is one way, downlink. So uplink also another 230 dB. So almost 460 dB loss you have just for propagation losses. So that means your power per channel you don't want to increase too much, because then the satellite cannot handle. So that's limited. So the gain is a key factor. So all pressure is there on antenna engineer to maximize the gain, both on the transmit and receive antennas. So even 0.2 dB gain makes a big difference. So it's either you win a proposal or lose a proposal. So that's why you need to really optimize the gain. That means you have to maximize the directivity and you have to minimize the losses. So you have to find a way. Types of antennas, I think typically you have feeds, either horns, helices, bicones, patches, slots, dipoles, monopoles, stacked patches. We've all these for ultra wideband applications, bow tie type elements. So these are typically low or medium gain. Then you have different types of reflectors. I think the list is limitless. Paraboloid reflectors or shaped surface reflectors, offset fed reflectors, GL reflectors, Cassegrain type, Gregorian type, axially displaced ellipsoid type. Each one has its own advantages. Center fed reflectors, gimbal reflectors, hyperbolic mesh reflectors, composite graphite. Typically, to withstand the temperature, most of the reflectors are made of graphite, composite graphite, because it's thermally stable. And these are used for high gain or super high gain applications. You need very high gain for military applications. So that's why I call it super gain, maybe 60 dB or even more. Phased arrays are used. They're used not all the time because reflectors are cheap. They're about cost about $2 million, whereas phased arrays cost about $15 to $20 million, depending on the complexity. So they're almost about 8 times more expensive. So that's the reason you use them only when needed. For example, for military purposes, if you want to adapt your beam or so, then you have to use the phased arrays. So they have square lattice, hexagonal lattice, fractal type, thinned arrays, and DRAs, direct radiating arrays with a beamforming network behind. So that's a fixed beam. So whereas most of the phased arrays, your beam scans over a certain coverage region. So you need to provide that. So it's not super high gain, but high gain and medium gain it can provide. So there's also hybrid antennas, which are a combination of phased arrays and reflector antennas. So for example, reflector array, generally it's not used in space because of, like I said, ESD, and other thing is it's very narrow band and it cannot provide 33 dB cross-pole discrimination. So that's why for most of the satellites, you don't see reflector arrays. But the ground applications and other applications, people, even space applications, people have used them. So, but very limited. But if you have to use reflector array, then don't use patches, use metallic patches so that you don't have ESD problem. Confocal, so that's also important because that's a phased array feeding a reflector, mainly a parabolic subreflector, and then you have a parabolic main reflector. So scanning of the phased array will give beam scanning coming out of the reflector. Then you have imaging reflector where it forms a larger image of the feed array on the reflector surface, and it provides limited scanning, but some cases it's used as well. So there's hundreds of configurations, so you should know which design to use for a given application. So I won't go through, but you can refer to the paper here and also my book. So basically it shows square lattice, hexagonal lattice, and all the performance you can analyze probably within 1 hour. So if you know the requirements like frequencies, coverage, etc., I think you can design the phased array probably within 1 hour. I think right now we have developed the software to design the phased arrays and also to analyze the phased arrays quickly. So both in MATLAB and Python. So it takes probably 30 seconds or so to design and analyze completely. So that's the speed I think you need when you're in the industry. So why you use phased arrays? Because it gives the flexibility of the beam operation. It's a low profile, but lower efficiency, because power added efficiency coming from SSPAs is very low, probably 25%. That means 75% of the energy is dissipated as a heat. So you need to have good heat pipes, and you need to control the heat so that you can dissipate through radiator panels. It's higher cost, so you use occasionally where it's needed. So reflector antennas, I think this is one configuration I'm showing on the bottom, offset fed parabolic reflector with a single feed. So there I think you need to provide proper illumination on the reflector surface to maximize the gain. So typically about 12 to 15 dB is used as a taper because you need to minimize the power going outside the reflector. You want most of the power captured by the reflector. So and then you don't want to taper too much. If you taper too much, your aperture efficiency goes down. So the overall efficiency, what you see on the right side, on the curve actually on the left side. So it for a given reflector, you can see what is the horn size you need to use to provide certain taper. So maximum efficiency you can get with a reflector system is about 80%. So you need to check all the time the efficiency. Sometimes people run the software and leave it. So if it is even 60% efficiency, that means it's not good, not properly designed. Always check the efficiency. So you can probably read more about the design in the book. So these are the 3 volumes published in 2013. Myself, Professor Shafai, who was my mentor long time back, and Satish Sharma, who is a professor now at San Diego State University. So we have written 3 volumes: Application of Reflectors, Theory and Design of Reflectors, and Feed Systems. So you can refer to a lot of literature is available there, so you can go through. And some practical antennas are also discussed. So EHF payload, I want to show this because this advanced EHF payload, basically it works at 20 gigahertz downlink and 45 gigahertz uplink. And it has about almost 16 antennas, and there are 10 of them are reflector antennas. 3 of them are phased arrays, 2 downlink phased array or transmit phased array, 1 receive phased array, so which works at 45 gigahertz, and that's the most critical component of the whole payload, because it's need to adapt its patterns to prevent multiple jammers. So you need to create nulls at the location of the jammers, and so you need to adapt the patterns pretty fast so that ground jammers cannot sort of jam signals and make your satellites space junk. So you need to avoid that. So this is the phased array on the right, you see. So it has about 400 horn elements. So on the top is the thermal cover. So that's important to protect the or minimize the temperature variations across the aperture. Then you have down converter, and then you can see the heat pipes. The heat pipes are actually going down, and on the radiator panel it dissipates. So you convert into higher frequency, which is C-band, and then you have down convert directly after that to digital payload. So all the phase shifting, amplitude tapering, everything is done through variable phase shifters and attenuators at the digital level, and the combining as well. So it produces about 8 beams, different shapes, spot beam or area beams it provides. So because you can adapt the beam to any requirements we have. And I'll show some video here. I hope it works. Let me see.
The advanced DHF payload.
Okay, so you see how the satellites are operated, especially this one for military applications. So I think, how much time I have? I think I have still a lot of material.
Yes, sir. Please continue.
Okay, so these are the hardware examples. what you see, I think once, of course, you design, but then you want to see some hardware, how it looks like. So on the top left is how once the satellite is on orbit, how they're deployed, all the reflectors are on the there. Here, I think it's shown like 5 reflectors, one on the native panel, 2 on the east side of the spacecraft, 2 on the west side. These are large reflectors, go 100-inch to maybe 120 inches maximum. Then before launch, I think you see in the middle how the satellite is put into a small area, which is like typically 4-meter fairing, so that you can put in the launch vehicle and then you can launch the satellite. So once in the orbit, actually, the reflectors are deployed and into the proper shape through activators, and then solar panels are deployed, and then the antenna starts working. So you can see some of the horns on the right side. There's a feed assembly, which is, in this case, this is both works a C-band downlink and uplink. So 3.7 to 4.2 gigahertz on the downlink and 5.95 to 6.425 on the uplink. So one single feed covers both bands. And then it has 2 polarizations for each, right hand and left hand polarizations. So you can see 4 ports there, 2 are for transmit, 2 are for receive. Then inside you have polarizers, you have filters, you have transitions to match the. So when you measure the whole feed assembly, I think you should get return loss of more than 22 dB, which is typical spec. So we don't design for 10 dB or 5 dB return loss. You have to design at least for 25 dB return loss. Then, of course, with temperature, it changes a bit. So you can meet a 22 dB return loss requirement. And then you have bicone antenna. You can see the command bicone and the telemetry bicone. One is on the top of the other. So these are slots around the bicone. So it provides uniform illumination in the azimuth, and it has certain elevation angle, which is typically works 90 degrees from whatever the comms signal. So that this is very important because it works in the transfer orbit. So that's the only link you have in the transfer orbit. When the spacecraft is flying, that's how people on the ground can communicate and see the health of the satellite, how it's turning and how it is working in the transfer orbit. So that's, though I think it's not very sort of looks complicated, but that's also very important. If that fails, you don't have the satellite. So that's very important. And then you see the large mesh reflectors. So nowadays you can design up to even 40 meters or 50 meter size, depending on your requirement. So these large size mesh reflectors are needed for low frequencies, especially mobile satellite applications, which are at L band and S band. So this is a mesh which is very lightweight mesh. It's made of gold-plated molybdenum material. I think these are like thin wires of 1 mil in diameter, so bunched together. So the mesh needs attention, so it is provided with a truss type structure and also with a back umbrella type structure to support it. It has certain openings per inch, so most applications have 10 openings per inch at low frequencies. But nowadays people want to use for high frequencies, so you need to have at least 30 to 40 openings per inch. So that means mesh becomes very dense. And then before launch, you sort of fold it into a compact structure like what you see on the black structure here, like a cylinder. And this is a quick video you want to see how the mesh reflectors are deployed. This is the Delta launch for Vandenberg space. So this is launched in the lower orbit, 680 kilometers, polar orbit, basically. Monitor the moisture as well as the depletion of the icebergs. So we build the mesh reflector for that, Northrop Grumman. NASA was made the whole payload. Can see the separation now. So once in orbit, then first thing is to deploy the solar panels. So now you see the deployment of the mesh reflectors. So it has to be done very slowly. So and then the black cylinder deploys like an umbrella. And since it's in a polar orbit, it rotates at about 35 RPM, conical area, so provides a swath of about 1,000 kilometers on the ground. And based on the returns, you can see what is the moisture content from the soil or icebergs and how the icebergs are depleting. So it's a conical angle is about 35 degrees, and I think it spins at 15 RPM. So it basically shows the mechanical complexity of the system, not just the RF electrical design. So both are important. Can you hear me?
Yes, sir. Yes, sir.
So the next part is how to publish papers. I think I'll go through quickly. So conference and the journal papers are both important. Each has its own merit. If you go conference papers, I think you have IEEE APSFC, which is the main conference. This was held in Singapore in 2021. And in India, you have MapCon, BAMS. And then in Asia, you have APCAP, ISAP. And in Europe, you have UCAP. These are the main conferences for antennas. In journals, we have transactions on antennas and propagation, AWPL, antennas and propagation magazine. Then you have IATE, or now it's called IAT, and proceedings IEEE as well. So conference publications are important because you attend the conference, you present your paper, you network with others, you talk to them, and networking is very important. That's how you know what people are working on. And journal publications get professional recognition, so of course, but conference publication is also very important. So quality is more important than quantity. People say that, oh, I have so many papers, but I think you need to, quality is more important than the quantity. I mean, one good paper, if you publish and a lot of people cite and follow it, then I think it's considered a good paper. How to publish? I think basically don't rush your publication. So take it easy, prepare well, do the literature search, because you need to see what people have done and how your paper is different from what was done in the prior art. So identify the novelty. So unless there is novelty, it's very hard for reviewers to accept, because just a minor improvement of some of the papers is not sufficient for it to qualify, because nowadays we get a lot of requests for publications, a lot of papers to review. So I have to select, of course, number of pages are limited. So I have to select the good ones. So that's why novelty is important. Keep it short and sweet. Don't write lengthy pages like 15, 20 pages. Whenever I see papers like that, I think it sort of it doesn't give a good feeling. So you should be able to convey the message in very, doesn't have to be a lengthy paper. You can write a very good paper in about 7, 8 pages, or because it also gives others also a chance to publish. So if you take away the whole publication yourself, I think it's not very good. And people don't read most of the time. If lengthy papers, very few people read. Figures and tables are important and they should convey the message. So make a good quality figures and tables. English is important because grammar and writing style, short sentences, etc. So sometimes you may not be good in English, but you get reviewed by your co-workers or professors or somebody who is good in English. So I think get it reviewed independently. So you need to revise a lot. So you do a couple of revisions, and once you're happy with your paper, then only you submit. Don't just finish writing and then submit. Initial submission will have a lot of errors. You don't want the reviewers to point those mistakes. So just be cautious. Contents, like I said, keep it short. Abstract conveys you should convey the novelty in abstract itself, because that's the first thing reviewers read. So unless they find novelty, I think it's very hard to accept the paper. Introduction, I think importance of the work, applications, prior work, extensions or new work presented in the paper. Main section, typically 3 to 4, which takes care of design, analysis, test results, fabrication, and the comparisons with prior art. Summary, conclusions, and acknowledgements. And then references. I think don't just add the references for the reference sake, but really the papers which give value to your paper and which you referred. I think you refer. Sometimes people tend to give like 50, 60 references, whether they referred or not. So it's not a good habit. So this is one of the paper a lot of people sort of consider as, I think it number 1 in 2020 when we published. I think it was ranked number 1 paper. So you can refer that and you can see why it is, and not just because of my paper, but it's also, this paper is written with an intern, so who worked with me for 2 years, and then he's now doing great things in Amazon. Submission, use IEEE format, double column. I think I recommend 7 pages or less, not more than that. Once you submit, EIC will allocate the paper to associate editors. EIC is the editor in charge. So it takes about 1 week. Then AE goes and assigns to 3 to 4 reviewers to review a paper. So that takes about 2 weeks. Then reviewers are given about 4 weeks to submit their reports. So typically it's accept. If it is very good paper, then people accept. It's very rare though to get accepted in the first shot. Then minor revisions, major revisions, reject. So some have reject and resubmit, like AWPL. So if you might sort of reject the paper in the present form, but you can, if the paper has some merit, you can ask them to resubmit by following certain suggestions from the reviewers. Minimum 2 reviews are required. So if the reviews are not consistent, then you send to a 3rd reviewer. So that's about 2 weeks. Then associate editor summarizes and makes recommendations to EIC. That's about 1 week. So then EIC makes the final recommendation and sends letters to the corresponding author. So that's about 1 week. So total it takes about 4 months for the first recommendation. So then if you have to review, then I think it will take another 2 months. Sometimes 2 revisions are needed. First revision may not be completely satisfying to reviewers, so then you have to go through 2nd revisions. So that's why first submission is very important. So take time and make sure that you're happy with your paper. So once you publish your work in any journal, that feeling is very, I can't explain. So it gives utmost satisfaction to the author. So when you see your first paper published in international journal or conference, I think that's important. So then it motivates you to write more. So, but be careful not to overpublish, like a lot of people do. So including myself. I used to publish a lot, but now I'm very careful, so I don't publish that much unless it's a good quality. Good paper with a lot of citations is worth more than 10 average papers, so without citations. So there's a lot of competition, so I think some countries like, I don't want to name, they pay heavily for others when they publish in IEEE. So you can see nowadays a lot of papers coming from this particular country because if it is accepted, they pay equivalent to something like $3,000 to $4,000 US to the others, the country pays. So that's why in the process, I think they submit a lot of papers and you have to be careful as a reviewer. Do good work, prepare well, and good luck with your first publication. So that's very important. Doesn't have to be, you need to graduate to write a paper. I think people started writing even in the first year of BTech or second year. So get more motivated yourself. And if you think that you have done something important, maybe you can try writing a paper for a conference and then maybe publish it as well in a journal. So innovation, I think next topic, I think probably last topic I'll go through. So it's a process of translating an idea into goods or services that create value for which the customer will pay. So that's important because if the customer cannot use your invention, then it's not worth it. To be called an invention, idea must be replicable at an economical cost and must satisfy a specific need. So need should be there and novelty should be there, and it has to be more like a product oriented. So IEEE mission statement, basically, you can read the mission statement. So it's basically foster technological innovation and excellence for the benefit of humanity. So that means whatever you innovate, I think it has to be some benefit to the humanity, whether to the users, user community, or some technical community, or some industry, or any other purposes. Internet, for example, providing internet in areas where they don't have proper signals via satellite, that's important. So what is innovation? So innovation is not an imitation. So it's not just imitate something else and do minor improvements. It has to be, novelty should be there and it should be out of box idea or concept. So invention is the result of innovation. So you start the innovation first, you get the ideas, and then you start preparing the invention. So inventions, why people do? Because they're protected by, your technology is protected by patents or trade secrets. United States Patent and Trademark Office, or India, you have similar thing. Each country has, Europeans have their own patent office, India has patent office. So how does it happen? I think most of the time it happens by necessity. So you need to develop something to meet customer requirements, which current designs cannot support. So you need to invent a new one. Sometimes it happens by accident. You're sleeping and some idea comes for you. And then you suddenly wake up and documenting what the idea. And in the next day or next week, I think you start working on that. So sometimes it happens by accident. And also planning. Proper planning is also sometimes necessary. End product of invention is an improved product, a patent, or a trademark. We all have innovative minds. It's not like only one particular type of people can innovate. We all have, but then we have to channel our thoughts in a more focused way. So this I have shown before. Innovation distinguishes leaders from followers. Steve Jobs quote. Why innovate? So there are company benefits. There are also societal benefits. Sometimes you get royalties, so you get some money as well through the company. When your patent is used by your competitors, they have to pay royalties, so you get some money there. And more importantly, it's advanced technology or product. For example, iPhone, GPS, they're all great inventions. Professional satisfaction, that's important, engineering pride. So more than the money, I think that's important. If you get a patent, I think awarded to you. So that means it's a lot of pride, I think you can take in that, because it's not easy to get a patent, unlike the paper. So passion and personal satisfaction, that's important. So like this I show many times, engineers innovate and researchers publish. So not that engineers cannot publish or researchers cannot innovate, but that's their basic, most of them do. Engineers in the industry, they need to innovate, and if you're in the academic field, you need to publish papers. So patent versus paper, what's the difference? So technical paper, it's a result of research, you do analysis, improve design, etc. It's a science. Patent is the result of engineering a new product. Science versus engineering, both are important. You cannot say that one is more important than the other. So engineering, so it's understand the requirements, think outside the box. Persistence, teamwork, sometimes you have to work with a big team. Product development with new capability. So this patent is worth several publications and more, because patent takes almost about 4 years to get awarded and go through a lot of reviews, not just one review or so. So I think that's why I say patent is worth several publications. A simple question. So somebody invented pencil. I think that's good. People used to take a pencil, and if what they write is wrong, they take eraser separately, and then they sort of erase it and rewrite. So then somebody came up with this idea of putting a rubber on top of the pencil eraser. So question is whether B can be patented. So answer is yes, because it's added capability. So it's eraser and pencil in the same hardware. So that one got a patent awarded. So I think basically innovation or patenting requires a lot of hardware experience, because you need to provide the novelty and the end user. You need to satisfy the end user requirements. So it actually needs to be disciplined, because you need hard work. I think issued patents come once in a week on Tuesday, and applications come every Thursday. So there'll be something like about 500 or 600 patents. So you need to go through all of them to make sure, if you're interested, what other people are doing, so that what their idea is, and whether you can improve the idea or come up with a new product. So that's takes a discipline. I think at least once a week you need to go through patent office issued patents or trademarks. So patent is outcome of innovation. Complete the work first and then think of patenting, or not later. So you have to do the work first. Procedure, I think USPTO, European Patent Office, World Patent Office, a lot of things. So file an invention disclosure with your company first to get approval. Selected disclosures are filed for patents. So only few are approved for patenting, because each patent costs about $20,000 for filing, lawyer fee, etc. So companies are very selective. So you need to prepare a PowerPoint package and attach with the disclosure what novelty is, and then patent attorney uses your package and draft it in his language and file an application with USPTO. So USPTO, for example, examiners will review. Typically it takes 3 to 4 years for a patent to be issued, whereas paper takes less than a year, maybe 6 months to 1 year. So you can see how long it takes for a patent to get issued. I think title, I think abstract, and then background, prior art publications you need to describe. Detailed description and drawings. Drawings have to be made, what is new about and what parts are new. Claims, I think typically you have 20 claims. So generally you have 2 or 3 major claims, and then there is a subclaims. So total, I think you have about 20 claims. Broader claims are preferred, because then you don't narrow down the use of your hardware to a particular application only. Patents that are most difficult to copy are highly beneficial to companies because they bring royalty, and competitors cannot copy that. Type of patents, provisional, so validity is 1 year. So initially you apply for a provisional patent. After it's approved, then you file for a utility patent. So utility patents are mostly preferred because validity is 20 years. Design patents are okay, validity is 15 years, but they don't protect the functionality of your hardware. Trade secret, sometimes a company doesn't want to disclose. If you write a patent, that means it is approved and it's in USPTO, then others can read and they can see what this company is doing. So sometimes they want to protect it, so then it's a trade secret. You apply for a trade secret and you get it. So this is a typical example of one of my patent. What is novelty in this case? Before, there used to be different antenna designs depending on the orbital slots to cover, say, for example, certain region corners. So going from 70° west up to 120° west orbital slots. Every 2 degrees, one slot, right? So people design different because shaping is the coverage area changes based on the orbital location. So they used to have different designs. So this particular thing is designed over a complete orbital arc. One design basically covers all the orbital slots. So that's issued. And I think it has been used on maybe more than 20 satellites. Significant cost saving because one design covers all the orbital slots. So used for fixed satellite service and broadcast satellite service. I'll show some examples of advanced hardware. I think we finished our talk, but I think you have seen this. These are multiple spot beams to cover the local channel broadcast. So you can see each. Any question? Hello? Any question? Okay, if not, I'll go through maybe at least another 5 minutes.
Sir, please continue. Yes, sir. Sir, please continue.
So these multiple beams are this first time I think we sort of developed when I was working at Boeing Satellite Systems. Customer came and they wanted those days. I think it's all local channels, national channels like ABC, NBC, etc. But then people want local channels. So how to give local channels? I think they came with a requirement of whole CONUS is divided into 216 designated market areas based on population density, etc. Like New York is number one. Los Angeles, where I live, is number 2. Number 3 is I think Chicago, etc. So they want to cover a top 60 of 216, and then so if you start actually, they worked with another manufacturer before, and they couldn't come up with a design. So then they came to Boeing Satellite System, and I was asked to work, and then within a week, I sort of showed them how to cover all 216 DMAs with minimum number of beams. So each color beam is one frequency band. You divide the spectrum into 3 or 4 bands and keep reusing them. So that way, the more reuse you have, you can cover more DMAs. So we cover all 216. They were really surprised and signed the contract within a month. So then this is the first direct-to-home broadcast satellite that designed for local channels. So then a lot of other people, Europe and India, now using this multi-beam technology to provide the to reuse the spectrum many times so that they can support multiple spot beams. So these are some phased array hardware you have seen. So different types of you can see on the right, it's a bow tie type element. Then in the middle, you see rigid element array. Then you see on the bottom is the stacked patches. And then on the right side, you can see conical Vivaldi. So that provides 1 gigahertz to 18 gigahertz frequency, very wide, ultra wideband spectrum. So this is quad band petal reflector for ground applications. So this is portable by soldiers, so they can sort of, all the reflector is made of 6 pedals. You can see the pedals, so they can remove and fold and carry it in a briefcase. So that's one, and then a sub-reflector in the feed is one assembly, and then it's gimbaled and it's mounted on a tripod, so which is made of graphite. So it's very lightweight, so that the soldier can carry, and also packable. So once I think everything is assembled, you can see on the right how it looks like. So you have a tripod, you have a gimbal, 2-axis gimbal, which can scan plus minus 70 degrees. And then you have pedal reflector to provide the gain. This is to communicate with satellites and aircraft. So when the soldier is on the battlefield, so he can sort of deploy when needed and immediately communicate, and then pass the signals to the ground operations to take any action. So it's a low mass, low cost. It's about 10 pounds. It costs, I think, on a unit basis, on a quantity, it costs about 200K or something, maybe less than 200K. We supplied about, for field testing, 3 of them. I think they're currently being field tested by US Army. And once I think everything is fine, I think we'll get to make in a bulk quantity. I think millions of units are needed. So we have a patent on this, and it's published in AP magazine as well. So this is called bunker antenna. So when the soldier is on the ground, or he needs to communicate with the main office and also to aircrafts. And then once he need to take some action, so the antenna needs to be deployed from the folded configuration to unfolded configuration. So antenna you see is on the top middle. So that's basically antenna with a radome, protective radome. So that's deployed between 2 states, horizontal to vertical, and it's omni type antenna. So it can provide very wide bands. I think it covers Ku band to up to Ka band, more than octave bandwidth, and very lightweight and very compact. And the reason it's deployed higher is because you want to minimize the radiation going onto the head. So there are some requirements you have to meet. This is the ultra wideband segmented antenna for maritime application. So they need to use a whole spectrum to get maximize the capacity of the maritime system, ground system, 1 gigahertz to 60 gigahertz. And there's no, people try to use Vivaldi's. You need to meet the gain, you need about 10,000 Vivaldi elements, but then they cannot meet the bandwidth. So Vivaldi typically meets 1 gigahertz to 18 gigahertz or so, up to that 18 to 1 ratio. But here we need 60 to 1 ratio. So we segmented into 3 bands: low band, mid band, and high band. High band is the reflector. Low band is Vivaldi type, or and then mid band is a horn with everything has to be compact. I think it has to meet less than 20 inches in size. So we made into 19 inch by 19 inch. So then the gain of the mid band is not sufficient. They want to improve by 2 dB. So we put a lens on top of the horn to meet the requirements. So this is the ring antenna for advanced missiles, which I was working till last year, finished the critical design review. So you can see this works at L band, GPS bands L1, L2, and also S band, which is command and telemetry, provides telemetry signal. So when you have 3 rings, a good thing here is there's no patches or any elements. It's just a metal sheet with a gap, and then you excite the metal sheet at different points in sectors, and you combine the 6 sectors into one with the coax cables inside the cylinder of this vehicle. So this is all thermally protected. So because in the launch, the missile goes up to 1500 degrees C or so, you need to protect. So that's why there's no dielectric we use. We basically use metal. And then there is a coupling between L1 and L2. So we provide RF fences to minimize the coupling. And key thing here is the phase variation has to be very tight, less than 2 degrees over 360 degrees. And the elevation coverage is about 160 degrees, almost providing 4 pi steradians, 90% of 4 pi steradians. So that in order to meet that 2 degree phase variation requirements, because that determines the accuracy of your vehicle from the ground you can track. So that's the most difficult. And then beam forming is simple. So you can form 6 sectors into one. And this is the last one, I think, ground antennas. I think US Air Force has currently, on the left side, what you see is works at Ka band and LNS band, which is separated by a frequency selective surface. So basically, frequency selective surface is transparent to lower frequency and reflective at higher frequency. So now they wanted to add 7 more additional frequency bands starting from C band to upper Ka band up to 35 gigahertz. So you can't do that with the frequency selective surface. So they went to the supplier of these ground antennas, which is VSAT, and asked them. I said, no way we can add more frequencies. So then they came and talked to us, and we said that, okay, we can do that. Can maintain the same infrastructure, main reflector, everything behind. So then cut out the struts, take out the lossy feed on the top, LNS band, and then take out the struts because they cause gain degradation. So subreflector is supported by your feed cluster cone. And then feed has special features. You can see on the top right corner how the feed is integrated. So basically we use the same main reflector, but then put this, take out the old feed and put this advanced feed. And then we pack all the RF electronics behind, all the circuit boards, amplifiers, everything within that, because it's very compact compared to the previous design. So we delivered about 5 units and everything is working, all the frequencies, and the challenges are instead of one tracking, we have 2 tracking signals, one at Ka band, other at Ku band. So everything works. Now there are hundreds of ground antennas we need to modify. So I think people are working on upgrading all the ground antennas. 3D printed antennas, I think people started working on 3D printed antennas. I think they're known to be a bit lossy because of the aluminum, magnesium, silicon alloy. Silicon basically is lossy part. So, but there's new manufacturing technique, all metal using aluminum itself. So this one is supports on the left side Ka band, Ka band. So it's designed and built in 5 days. So advantage of 3D printing is its fabrication is very fast. So once you have the design, you can sort of give it, and then you put the powder, and then with the laser thing, you basically pack the powder in the required shape you want. So you get very good tolerances. You don't need post machining. At the same time, your losses will be pretty close to aluminum. So you don't have additional losses. So this is the new powder. I think a lot of metallurgical development have been done, and we used. I think it has been flying as well. So you can see the return loss is very good, like just like normal machined part. And then you can see on the right side the tracking for a 4-element monopulse tracker. The null depth of 45 dB you can achieve. So that shows how good the 3D printed technology is. So what are the advantages? It's lightweight compared to regular hardware, and also its cost and schedule is, I mean, you can save like 10 times more cost and more schedule using 3D printed. I think that's the future. I think a lot of people are now going into 3D manufacturing. And of course, whatever you build, you have to test it, antenna ranges. So at Northrop Grumman, we have 15 different ranges. Largest is 50 foot by 50 foot planar near field, and then 12 foot by 12 foot planar near field for smaller antennas. Then bistatic range to characterize the materials, and then spherical near field to measure the medium gain to low gain antennas, and then the compact range with the 6-foot quiet zone and anechoic chamber. All these things are needed. And then this is the last slide, I think. This is some comment I sort of made before. So there seems to be a big gap, not just in India or Asia, it's US as well. So all the question is whether universities are providing proper training to future engineers. The answer is no, because software, if you take, I think people are happy to do HFSS, CST, FICO. They're important, but at the same time, the real world is sticker grasp, which is basically used to design and analyze the reflectors. Mission, SHAMP, they're used to design the feeds and feed systems. Cobra, that's mainly used for Samount, they're used for aircraft antennas. Spark 3D for power handling. So all this software, I think most of the people probably didn't hear before. So when I talk to some students coming from India, I think what most of them are familiar is HFSS, but the real world is totally different. I think you need that, but you need to learn other software as well. And hardware, typically people does patches, slots, and reflector arrays, which is hardly used in space. So real world is horns, reflectors, and for space, air, or ground applications. So India has a great talent and luxury of large industrial base like ISRO, DRDO. If you talk to ISRO, I think people basically ask you whether you have reflector experience, whether can you run some codes and design antennas. DRDO, same thing. So Ground Observatory, RRI, Raman Research Labs, TFRL, Samir, Qualcomm, ECL, Bell. So all these industries need some experience with other types of software than what you have been using. And sometimes university, industry, government collaboration helps to remedy the situation. So the picture what you see is basically government provided funding to train the university guys. You see some interns actually from the university working with me and working with small industry like custom microwaving on the, you can see the CEO on the right side. So we worked for 3 years and basically trained the students, and once the student graduate from the university, we hire them. So all of them are hired by Northrop Grumman, or a couple of them are hired by other industry as well. So they get the right training and they sort of work with you, come every day and ask questions, and then you tell them what to do and they go and they sort of learn. So that way every summertime they come as interns, and some came about three terms as from second year, third year, fourth year, and they're now employed by Northrop Grumman. And such an arrangement actually I have been advocating in India as well. I think there is some ways. ISRO says, yeah, they support universities and some small industries as well. So I think more and more we have this, I think it will be good for students and the industry as well. So this is the conclusion. So I don't want to be. So be innovative and try to be engineer rather than a researcher, because we are all engineers. We're getting engineering degrees, so we have to behave like engineers, not like scientists. So science also important, but that's a different field. So that's all I have. So now it is open for questions. You can ask anything. I'll try to answer. If not, I'll try to answer, email you. Okay.
Okay.
Meanwhile, I'll show the.
So,
Yeah, keep asking the questions. So I'll put it in a low voice.
Hello, sir. Hello. Am I audible?
hello.
Hello, sir. Am I audible?
Yeah.
Okay, sir. First of all,
I'm thank you to you. This is very nice lecture, and we will you will discuss all the different type of antenna and different basic concept and how to patent and how innovation. What's the role of engineers in this in this society? This is very good. But sir, I have a doubt. Suppose I have a noble work and we want to publish and patent both. We can publish and patent for that work. If yes, then how?
Yeah, I think when you want to patent and publish, I think you need to patent it first, because if you publish, then it loses the value because it's already in public domain. So you patent it first, and then once it's approved or patented, then you can sort of publish not all the details, but because it's all disclosed and protected. So for 20 years, I think you can publish it, but not the other way. You can't publish and then patent it. You cannot do that.
Okay, sir. Thank you, sir.
Yeah.
Yeah, good evening, Mr. Sudhakar. This said basically Pankaj Chawla, Senior Application Engineer, CST Jyoti Microsystem, hailing from IIT Jammu. So my question is like for the scan losses, what would be the threshold for that for the space applications?
Scan loss, it depends on the element size, because it's a scan loss is coming from mainly from the element roll-off. So that you can estimate very easily. So the phased array design looks complicated, but you can design phased array in probably a couple of hours. So you can select because people tend to, in the academy, I see a lot of papers, even for 30-degree scan, they use a half a lambda wavelength. So when you use that, I think the number of elements become very large, thousands or so, maybe more than that. But the main reason I think people use lambda by 2 spacing is because to prevent the grading lobes in the forward region. So that equation is also wrong, because that's mainly derived for radar type application, where you don't want any returns coming in the forward hemisphere. So that means your grading lobes have to be more than 90 degrees. So that's the reason lambda by 2 spacing came. But if you're trying to design for space, your coverage is a global coverage, plus minus 8.7 or 9 degrees max. So to do that, I think if you use that lambda by 2 elements, your number of elements becomes like 20,000 or something. So the cost goes up like exponentially with the number of elements. So in these cases, you need a grading lobes, but you need the grading lobes outside the coverage. So there's an equation for that. I think you can refer to my paper in the given in my presentation. And that basically allows you to use elements up to 3 lambda or 3.5 lambda. So that your grading, you want the grading lobes and you want the grading lobes to be outside the coverage region, which is plus minus 9 degrees. So you can put the grading lobes at about 12 degrees or 13 degrees so that they won't impact your scan beams. At the same time, you minimize the number of elements from 20,000 to probably 400 elements, which is much more manageable. And you get, so only thing is then, of course, since element is large, then your element pattern is rolls off quickly. So, but you want to make sure that you minimize the losses within when you scan the beam to 9 degrees. So that you can estimate very easily with the Gaussian beam analysis. You can refer to my paper. I think all the equations are there. So you can design any phased array with square lattice or hex lattice with defined grading lobe location and defined coverage and frequency bands. Okay.
Yeah, thanks. Yeah.
Okay, sir. Before going to the next question, I would like to request all the participants, please fill out the attendance form, which will be a helpful part to generate your certificate, which was shared in the question and answer session. Any other another question? So thank you very much, sir, for such a wonderful presentation on antenna design from basics to system design. working of satellites, paper writing, patents are their work. Uh, Almost in the 2 hours, you covered everything related to the antenna design work. It was very informative for all of us. So thank you very much, sir. Yes.
Sir, I have a doubt.
Yeah,
Yes.
go ahead.
Sir, good morning, sir. This is Lakshman from Raghu Engineering College, India. Sir, why is it important to keep antenna design simple? How does the complexity impact the overall performance and cost, sir?
No, complexity is sometimes people try to design, like I told you, the antenna has not just the horns or reflectors, it has a lot of other components like polarizers, OMTs, filters, duplexes, waveguides, flex waveguides. So all these components, if you design separately, like that's what people do. Okay, polarizer, I design septum polarizer, or horn I design separately. Then what they do is they integrate together. They put them with flanges connections. So that's a very complex design. It's difficult to manufacture, and RFI is it's lossy. So the idea is always to do integrated approach. You integrate most of the components designed such that avoid these flanges and make it more compact. And all this can be designed using integrated approach. And also a good thing with integrated approach is any mismatches you have, you already say, for example, there's a horn and there is a polarizer. Of course, there's a mismatch between the two because the scattering matrix are different. So with the integrated approach, you can sort of, instead of local optimization, you can do global optimization and get your hardware much more working, meeting the requirements, better RF, better. You can also make it compact because you have less flanges, flange attachments. So that way, I think you can probably make it. When I say simple, I think sometimes, like example I showed, the frequency selective surface, you don't need that because nowadays technology is there to make a feed with covering both frequencies like Ka band and S band. So why you complicate the hardware? Of course, the technology is maybe 30 years or maybe 40 years old. So those days probably that's fine, but nowadays new technology comes and you have to always try to see how to make it simple. So there's a big difference in cost and schedule compared to sort of these two technologies I showed you. Yeah. So not only
Sir,
simple.
Hanuman here.
Yeah.
Sir, what are the antennas you recommend for 0.2 to 2 gigahertz? If you want to design some for prime focus parabola dish for radio astronomy purpose.
So
what kind of antenna you?
Yeah, most of them are like Vivaldi type or 0.2 to 2, right?
Yeah,
so
0.2 to 2 gigahertz.
10 to 1 bandwidth ratio. So you can either use, I think I showed some configurations here, I guess. See here. So you can, this is a wedge element, sorry, rigid, single rigid or double rigid waveguide element. So that can give you about 8 to 1 bandwidth ratio. Whereas Vivaldi, you can see on the bottom right. So that's a conical element with Vivaldi type, but with the conical type element rather than Vivaldi, because the gaps will radiate rather than the conical element. So that can give you 16 to 1 or 18 to 1 bandwidth ratio. So probably that's maybe more suited to you, maybe a small portion of this array to feed your reflector to give you the right taper on at the low frequency. High frequency you get anyway good taper. So low frequency, I think you need to combine those signals anyway, right? So I don't know whether you're doing the beamforming digital or RF or IF. So it all depends on technologies. But antenna-wise, I think those can give you the 0.2 to 2 gigahertz, which is 10 to 1 bandwidth ratio.
Thank you, sir.
Some form of Vivaldi, yeah. You can try the rigid element also, because that's designed for 8:1 bandwidth ratio. Maybe you can extend to 10:1, because that's much more compact than Vivaldi, because Vivaldi tends to be too long, right? Okay. Somebody's asking.
Yeah, thank you.
So can UWB frequency range can be used for IoT applications, sir?
Yeah, you can use it, or you can use a different frequency for IoT. It depends on your IoT type application, what it is. I don't know whether I got your question correctly, but so what are the bands? Is it 4G?
From 3.1.
Is it 4G or
5G, sir. 5G. It can cover 5G application. It can cover. It can be used for 5G applications, sir. 3.7.
Yeah, I think 3.7 to 5.4. 3 point. I think it goes 3.3 to 4.
Yes, sir. Yes, sir.
Yeah. So that's about 90 megahertz, right? 900 megahertz, 3.3 to 4.2. So that's almost like 25% or 30% bandwidth.
Sorry, sir. I achieved the bandwidth from 3.1 to 10.1 gigahertz, sir. But it resonates for three frequencies: 3.6, 5.6, and 8.7.
Yeah.
But that can be used for IoT application.
Yeah. You can definitely use, but depends on how you use it for IoT type. Sometimes people tend to use the whole, because 5G, the capacity is important. So instead of 3 different frequencies, narrowband resonances, people want a continuous band, so that they can design both the transmit and receive with wider bandwidths. So that's the bandwidth is proportional. Capacity is proportional to the bandwidth, right? So you need. So sometimes that's the reason 5G is even going into other bands like Ka bands, 20, 26 to 28, 30, 32, and 38 to 41 or something. So they're bands allocated for 5G, future 5G. But right now, I think people tend to use low frequencies, but future is mainly go to higher frequency where you get the bandwidth. And even low frequencies, people want to use continuous band, 900 megahertz band, right?
Yes.
So you are from?
I'm from Pondicherry, sir.
Oh, okay. Yeah, good school. No, Professor Prithviraj?
Sir, yes, sir. He is in Pondicherry University.
Yeah, he retired, and I just met him a few months back when I was in India.
Yes, I'm a research scholar from Manakula Vinayagar Trust, sir, Engineering College.
Oh, okay. Is Shanmuganathan there now?
Yes, sir. He's there, sir.
Okay.
Pondicherry University, sir.
Yeah, good.
Yes. Sir, can you suggest me substrates which can be used for the design of antennas? Normally, we go with the Roger material, or for a comparison, or if it is going to be a flexible polystyrene or a jean material, whether some other substrate can be used for research work, sir?
FR4, I think people use because it's commercially available and it's cheaper.
Yes, sir.
FR4,
to be different,
you can use it.
should be
RT Geroid 4003 is also people use quite a bit.
okay. In what way it differs with the 5.8, the other types of Roger, sir?
Other types depends. I think it depends on what epsilon R you want. Their Rogers have so many going up to 10 epsilon R of 10 or even more. So they're basically ceramic based. So I think it's expensive. But if you are in the Rogers, I think 4003 is highly used because it's cheaper as well. For university purposes, you can use FR4, which is more like a commercially available and cheaper than Rogers.
Okay, sir. I understand. Thank you, sir. Thank you, sir.
Okay.
Hello. Hello, sir. We are exceeding our time. Can we proceed for the vote of thanks?
Yeah. Oh, thanks very much for organizing.
Okay.
Thanks everybody
Sir,
for.
sir, we are inviting our volunteer, Mr. Tilakdhari Singh, to give the vote of thanks.
Hello, thank you, sir.
Mr.
Thank
Tilakdhari.
you for giving me such opportunity. Good evening to all of you and good morning to you, sir. I, Tilakdhari Singh, take privilege to extend a vote of thanks. On behalf of IEEE MNNIT student branch, I convey my deep regards and hearty thanks to our guest speaker, Dr. Sudhakar Rao, President and CEO, Rao S Consultant LLC USA, and the Senior Technical Fellow, Northern Grumman Space Systems USA, who, despite his very busy schedule, accepted our invitation as a speaker. Sir, I am confident enough that our participants would have highly benefited by your informative and inspiring talk about how to design antenna systems, publish your work, and patent your idea. I hope your thoughts and suggestions on antenna design system, its publication, including patent ideas, its scope, explained by you will motivate the research scholar to plan their career in this field. A special thanks to you, sir, for your valuable information on APS Society WAMS 2024 antennas in day-to-day communication, about antenna engineering, about antenna design by using software like HFSS, CST, Spark 3D, FECO, about SATCOM antennas and handbook on reflector antennas written by himself, and about AEHF satellite constellation video and academic training. Now, I would like to thank Professor V.S. Tripathi, Faculty Advisor, IEEE MNNIT Student Branch and convener of this event. I now thank all the participants for their patience and cooperation who joined this webinar from different regions of the country. A special thanks to our coordinators, Mr. Piyush Kumar Misra, Mr. Aditya Pal, Mr. Pawan Shukla, and Pooja Sharma to organize this event successfully. Once again, thank you so much to all of you for attending this webinar. Now, I stop my word with unique line taken from this slide. Science is about knowing and engineering is about doing by M. Vishwasaraya. So thank you, sir. Thank you again.
Thank you very much,
Thank you, Tilakdhari.
I think now we know how to publish papers. So you try to attend the WAMS 2024 in Vizag. Try to submit some papers and
yes.
Yeah. So you'll be treated well. So you'll get a free train ticket to Visakhapatnam. So everything. So write papers, good papers.
Sure, sir.
Yes.
We will join that webinar.
Okay.
Okay, sir. Thank you very much, sir, for accepting our invitation and for giving us such a wonderful presentation.
Okay.
Thank you very much, sir.
Really, thank you so much, sir. Thank you.
Thank you to all the participants. Thank you for joining with us. Thank you very much to all of you.
Sir, I'm unable to open the feedback form. Is it possible to send on email, sir?
Okay, sir. We will send out an email.
Tilak, sir, I'm unable to open the. Yeah. Is it possible to send by email, sir?
Hello, Adit. Are you here?
Yes, we will send out to you through mail. Okay.
Okay, sir. Thank you, sir.
Okay, thank you.